Okay, so even though you have just watched two videos about the introduction and about the basic formats of alternative null hypothesis, about the basic ideas, still we need to give you some examples to illustrate these ideas more concretely and show you how to eventually collect data and make a conclusion. So let's use this example in this video. I'm going to first conduct a two-tailed test in this video and then a one-tailed test in the next video. So recall our original problem. We want to test our production process. So suppose that we want to test the average weight in kilograms of our products. So we want to know whether mu is still 1000 or whether mu has become not 1000. Okay, suppose that in this example, the variance of the product weights is something we know is 40,000 kilograms square. Okay, or you know that just means the standard deviation is 200. Okay, the case with unknown standard deviation, population standard deviation, or population variance will be discussed in the next lecture. So today, let's just focus on the situation that we know what's the population variance, just for illustration purpose. Okay, you know this today, and then in the next week, you know how to deal with unknown variance. All right, let's come back. So a random sample must be conducted. So we need to have a random sample. That's the only thing we can use to do the testing. Suppose that our sample size n is 100 and also the sample mean x bar is 963. And now our task is to decide according to our observation whether this deviation, okay, we can see x bar is smaller than 1000, but we need to decide whether this degree of deviation is large enough for us to decide that mu is actually not 1000. Okay, so we collect the random sample as we did, and we're going to make our conclusion based on the observed sample. It is natural that we may be wrong when we claim that mu is not 1000. Okay, it's possible that mu is actually good, but unluckily we get a sample that is so extreme. That's possible, right? Because the sampling process itself is random. So what we want to do is to control the error probability. We want to control the probability that mu is 1000, but we say it is not. Okay? Or if you go back to think about example 2, we want to control the probability that this person is innocent, but we say he is guilty. We want to control this error probability. So that alpha be the maximum acceptable probability for us to make this kind of error. In statistics, alpha is called the significance level, and 1 minus alpha is called the confidence level. Okay, alpha typically said to be, for example, 5% or 1%. It decides how significant we need about the deviation to make a conclusion. Okay, and on the other hand, 1 minus alpha is the confidence level. If you think about the confidence interval we did last time, then you can see the analogy. Our target is that if mu is 1000, then our sampling and testing process will drive us to claim that mu is not 1000 with at most a probability alpha. Okay, if H0 is true, we're going to say it is wrong with at most a probability alpha. That's our target. Okay, so technically, how may we do it? Let's test with the significance level. Let's say it's 5%. Intuitively, if x bar is too far from 1000, we should reject the null hypothesis, right? So what's the logic behind it? If mu is actually 1000, if we see a very large deviation, that should be the probability should be very, very small, right? Very, very small. So if we really see a very large deviation, we have a strong evidence showing that mu is not 1000. Okay, and this is very important, so let me say that again. If originally, before we do anything, we assume the null hypothesis is right, and then if we see an observation which is very unlikely to occur under the hypothesis, under the null hypothesis, then we have a strong evidence showing that the null hypothesis is wrong. Okay, so that's the logic. So we start by collecting data and calculate the sample mean. Why do we calculate the sample mean? Basically, it's because we know the distribution of sample mean. That's something we need to control the probability. So we now want to construct a rejection rule. We want to determine a distance d so that if the deviation is greater than d, then we say we're going to reject H0. We know that d cannot be too large and cannot be too small. And in particular, if d is small, our chance to reject H0 would be larger. Okay? And then the chance to make a mistake would also be larger. So we want to find a d so that the rejection, the error rate is under control. Okay? Our task, in summary, is to calculate d. Okay, so now it's time to do some calculation. We want a distance d so that if the null hypothesis is true, the probability for us to make a mistake and reject H0 is only 5%. That means if mu is really 1000, we need d to make the error probability or the rejecting probability to be only 5%. This is the mathematical expression for this concept. And now, when we have this expression, typically we would ignore that mu equals 1000 and just write the former part when we want to condense the expression. Anyway, the key of calculation is that x bar is a random variable, and we know its probability distribution. Okay, that's the critical thing. So we know that sigma is 200, n is 100, and we have assumed that mu is 1000. So if mu is really 1000, okay, if mu is really 1000, then x bar would also have 1000 as its mean. And then, because sigma is 200, n is 100, this comes from sigma over square root of n. Okay? Finally, because we have the central limit theorem, and n is greater than 30, we know x bar is normally distributed. Okay, so this is a curve that draws x bar. The mean is 1000. We want to find d so that the two tail probability together is 5%. Or that means we want to find d so that for this normally distributed random variable, the left tail probability is 2.5%. Okay, exactly something you know how to do with normal distribution. Okay, so according to the fact that x bar is normally distributed with mean 1000 and the standard deviation 20, we actually can calculate d. D must be 39.2. Okay, So given that, we will have the tail probability, a two-tail probability to be 5%. Now that's something we know how to do. Okay, then we can construct something called the rejection region, which is the union of two intervals. Either x bar is less than or equal to 960.8, or x bar is greater than 1039.2. If x bar falls in either here or here, we say we reject H0. We say we reject H0. Okay? We do that. We reject H0 only when x bar is so small or so large. If mu is 1000, it's so unlikely to see x bar here or here, right? So we are so conservative so that we can control the error probability. So going back to our example, because x bar is 963, it's close to the rejection region, but it's not in the rejection region. So in this example, we cannot reject H0. The deviation from 1000 is not large enough, or we say the evidence is not strong enough. Okay, so in that case, we will not reject H0. So in this particular example, the two values 960.8 and 1039.2, these two numbers are called the critical values for rejection, the critical values for this hypothesis testing. Okay? If our sample mean in this example is more extreme than one of the critical values, we would reject H0. Otherwise, we do not reject H0. In our example, x bar 963 is not strong enough to support our null hypothesis. So now let's write down our concluding statement. Because the sample mean does not lie in the rejection region, we cannot reject H0. With a 95% confidence level, or sometimes people say with a 5% significance level, there is no strong evidence showing that the average weight is not 1000. Okay? Therefore, we should not shut down our machine and do an inspection. Recall that we are thinking about whether to do this. But once we do this, the cost is very high. So we should do that only when we have a strong confidence. Only when we have a strong evidence suggesting us that we should do that. Okay? In practice, you are the decision maker for choosing alpha. In this example, it's 5%. But if you care more about consumer welfare or consumers' rights, then probably you set alpha to be a larger number, 10%, 20%, 30%, depends, it's up to you. Okay? But the principle is the same. You first set up a error probability for you to control, and then you make the testing. One very important thing is that we should say there is no strong evidence showing that the average weight is not 1000. Okay? We cannot say there is a strong evidence showing that the average weight is 1000 grams. Okay? You know the two things are different. So as a summary, we want to know whether the machine is out of control. If it is actually good, we do not want to reach a conclusion that requires an inspection because that's a waste of money. So we will do that only if we have a strong evidence suggesting that mu is not 1000. We want to know whether H0 is false. Okay, so this is very interesting. We have H0. In general, what we are trying to do is to show H0 is false. If we can show it, we claim it. Otherwise, we make no conclusion. We control the probability of making a wrong conclusion. That's our alpha. Okay, because we want to make sure that we want to hopefully do not reject H0 when it is true. Finally, we will conclude that H0 is false if X bar falls in the rejection region. The calculation that we did, or the calculation that we depends on, is for we to have the normal distribution of X bar in that example. Okay, so this can be always, a normal distribution can always be transformed to the Z distribution, right? So that's why in this example we say we run the Z test. So you already have some ideas about confidence intervals and the t distributions, right? You probably can expect that in the next lecture we're going to tell you how to do this test when sigma is unknown. It's not very surprising that we will use a t distribution to do it, and that test would be called the t-test. Anyway, today we're talking about z-test, okay, because we are using the normal distribution. Lastly, let me emphasize again and again that these two statements are different. The wrong statement that many people would write when they first study hypothesis testing is that because the sample mean does not lie in the rejection region, we accept H0 with a 95% confidence. With a 95% confidence level, there is a strong evidence showing that the average rate is 1000. We actually do not have any evidence showing that the average weight is a certain number. Okay, all we did is to assume it is a certain number and then see whether we have an evidence to reject that original assumption. So what we can really say with evidence is that there is no evidence showing that the average weight is not 1000. So there is no reason to say we are wrong. There is no reason to say we are wrong. Then all we can do is to assume that we are still right. That's the principle. We still get guided about our decision making. Okay? But you need to know the difference. What we did, all we can say is there is no strong evidence showing that mu is not 1000. Okay? And we always say we can reject H0 or we cannot reject H0. We never say we accept H0. Okay? You see the difference. Cannot reject H0 means no evidence showing that mu is not 1000. It's different from having evidence showing that mu is 1000. Okay? Unable to prove one thing is false does not mean we can prove, we have proved one thing is true. That's the difference. Thank you.